thank you for joining us today. Our webinar is titled Digital Engineering Basics, Building the Product Model. My name is Bob Potok with Zuken, and I'm going to be hosting today's event. Just a couple of reminders. You are encouraged to ask questions. Please submit your questions in the question window, and we'll answer them during the Q&A session. We'll also be asking 3 polling questions during the webinar, and we're going to share and review the results so you can see how other attendees are responding as well. Your participation is greatly appreciated, and it's always interesting to see how everyone's responding. Just another reminder that this is the first webinar in a webinar series covering digital engineering basics. And the focus of this webinar series is really about product model development and implementation. And you may have picked up on the fact that we're going to use a video drone as the basis for the webinar series. The first one covering actually building the product model. The second one is getting into trade studies and evaluating the model in the context of implementation. And the third webinar is actually going to move the drone design from the model into a wire harness design process. We're also considering a fourth webinar that would actually cover the verification aspects of the product development process. I also want to give a special thanks to Vitech and to Phoenix Integration for co-hosting this webinar series. Let's take a quick look at the agenda. So I'd like to introduce Steve Cash. Steve is with Vitech and a principal systems engineer. He's going to be our subject matter expert. And Steve, what are you going to cover today?
Thanks, Bob. As the agenda says, and I'm going to literally read it, folks, is we're going to start with an overview of the systems engineering approach. We're then going to go and take that approach and build the video drone model. I'll then share the model with you, and we'll do some modification of the model. Or I'll teach you about how to share the model, and then we'll go into the model, review it, and do some modifications. And then we'll open up the floor for questions and answers. So Bob, I think we got a polling question, so turn it back to you.
Thank you, Steve. Yes, we do. And we just want to get a feel for what the audience demographic might be. So what is your current role? Are you a systems engineer, system product architect, electrical engineer, engineering manager, if you're other, if you would let us know what your role might be in the question tab, that'll just give us a little more information. So again, your participation is greatly appreciated. We're getting a great response for the audience. I'm going to let this run for a few more seconds as voting is still continuing, and then we'll share those results with everyone. Okay, why don't we go ahead and close it right now, and I'll share those results. So when we look at the results for what is your role, it looks like the majority are in a systems engineering role. Coming in second place is an other, which is a little surprising. And if I'm looking at the other, I see a supplier engineer, engineering research, PLM consultant, and so forth. Coming in third, engineering manager, and then electrical engineer and system product architect. So nice distribution of roles. Steve, any comments?
Yeah, I agree. It's a great distribution. It's good to see a wide range of active participants so they get a better idea of what we're doing in systems engineering and model-based systems engineering and how that can translate into their digital engineering environments.
Great. All right. Well, I'm going to close the survey and give the ball back to you.
All right. So as I said in the agenda, I'm going to start with an overview of the systems engineering approach. And mind you, I'm going to work from abstract to more detail as I discuss the approach, but this is a single approach. Every organization needs to establish their approach, but this is one that is been behind Vitech and has been proven and used for 50 plus years. So I'm going to start, wrong direction. Start with the very abstract, systems engineering likes to break things into two spaces. A problem space, which is where we talk about needs and definitions of what the problem is, and the solution space, which becomes then your implementation space. We can expand upon this and look at it from a slightly different perspective. There's the enterprise perspective, your business perspective. There's the operational architecture perspective, which is how does it work within its environment. There is the definition of the system, the black box perspective. The behavioral architecture, also called a glass box or white box perspective. And then the physical architecture perspectives. They each kind of bring a different attribute to the overall development. So as we move to become a little more detailed, we look at how this progresses with the engineering artifacts, if you will, for the design. We start with requirements. We use those requirements as the definition of our behaviors, what we want to do, and we start to allocate those into our architecture, the pieces and parts that do the work. We're going to talk about use cases today and how use cases can be used to refine your requirements, elicit more requirements. They also will help you in evolving your behavior. Along the way, in a model-based environment, we can connect all of this and capture your concerns and risks simultaneously. We won't cover that in this webinar, but I wanted to point it out is the model-based environment can help us do that. All the while, moving through various layers from top to bottom and breaking that behavior down, allocating it to your physical architecture, and working your way through the design. As we move from that process flow, we talk about a layered approach in systems engineering. And if you're doing top down, you're going to start at this top level. If you're doing reverse engineering, you might start at the nth level. But essentially, the process is very similar across the levels. You want to work from your requirements to your behaviors to your architecture and ultimately to verification and validation. And you'll notice I didn't talk about verification and validation in the previous slide, but it is a critical aspect of the overall process flow. So on the right-hand side of the screen, you'll see that I've put in some pictures to represent the levels. The top level is the universal view, a very, very high level view. And that's where we're going to spend most of the time today talking is from that perspective. But we will move very quickly through the physical architecture and talk about then the drone system view, the drone view, and potentially the parts of the drone view. So that's how we'll progress today from requirements and looking at the high level down to the physical architecture and the components. With that, Bob, I think we have another polling question. Oh, nope, got one more slide. Behind this and behind the process is the systems engineering meta model. Now, this is an information model that has been developed over that 50-year period. It started with the missile defense program at TRW in the 60s. It's an information relationship model. Many of you might be familiar with ASPICE and ASPICE traceability. ASPICE very much is focused on the idea of the relationship between artifacts and being able to demonstrate traceability, be it through change requests, into requirements, into your architecture, requirements from the system level to your software, and so on. In today's traditional world, this has been done in a document-centric way. An example of that would be CAD drawings having references to other specifications on them. You might do this as two disconnected Excel spreadsheets that have hyperlinks that connect columns between them. Or maybe they're not hyperlinks, they're just reference IDs from one spreadsheet to another. What digital engineering really enables is the connection of that information through those types of hyperlinks. And by embedding them in the data model and in the overall data files, you're able to click those links and transfer information directly. And it doesn't matter which side of that link you're on. If I was looking at it from a requirement or from a test case, I can click the other and very quickly pull the information. So it becomes this information model. What's important here is that this meta model establishes a map of those relationships important to engineering your product. The meta model that you use needs to align with your organization, your processes, and your information. With that, now we'll go to the poll question.
Thanks, Steve. Yeah, our second poll question relates to where are you in the digital engineering journey? The fact that this is a webinar series on digital engineering basics, we're curious to find out where are different organizations and companies, where are you with respect to that digital engineering journey? Have you not started? Are you kind of in a research mode? Have you gone into a deployment phase? Are you in full production, or you don't know? So again, we really appreciate everyone's participation, and I get to see some of the early results, and it is kind of interesting looking at the results. So keep those votes coming, and we'll be sharing those in just a few more seconds. Okay, all right, let's go ahead and close and share the poll. So where are you in the digital engineering journey? So by far the majority are in a research mode. Second most popular response is deployment. Then we move into don't know, production, and not started. So in some respects, I guess I'm a little surprised, but I'm not that surprised that the majority of the participants or attendees are in a research mode. Steve, based on your experience, are you surprised by that response, or is that kind of consistent with what you expected?
That seems to be pretty consistent with what I've seen. Kudos to all of you for investigating and looking to move forward with it. But that's pretty much in line with what I've seen.
Great. Yeah, that sounds good. All right, let me pass it back to you.
Okay, as I pointed out in the process flow, kind of the first step in this is collection of requirements. And in this case, we're going to talk about the video drone and potentially marketing requirements that come in and define, what marketing thinks we're looking for. And they're the best voice of our customers, so it's good that they've collected the information. So some of them here, cost, folds into a travel bag, they wanted to be remote controlled, streaming video to the phone, so on and so forth. This is a starting point for requirements. What we want to be sure to do is capture those, and we want to be sure to capture those as good systems requirements. And so GENESYS, our tool, is capable of that. But what's really important is talking about what we do with them. And so that's kind of the next step. Is if we talk about the specific requirement of folds into a travel bag, well, why do they want that? What are they really trying to do? So our goal as systems engineering would be to transcribe that a little bit and make sure we capture what they really intend. The video drone system shall be compact enough that the user can transport and use the system without limiting their ability to perform typical outdoor activities. Hey, now we've got a little bit more detail about what they really want with that requirement. We can go further, and as the engineering community, we want to get more detailed and more specific. We can take it and say the video drone system shall have dimensions of XYZ. Now, we may have done some sort of market analysis of other products. We may have done some research to pull that information. But again, that's our journey of requirements, is to get it to a point where we can analyze it and verify it. The next step would then be more in the detailed design phases and trying to figure out our solutions. But I put them here for reference to kind of give you an idea that you could then take it and say the remote control shall have a dimension, the drone shall have a dimension. Within GENESYS, there are multiple ways to view diagrams, and actually in the industry, people are looking at diagrams and different views of the same information. So here I just wanted to show that you have the ability to look at requirements in different ways. Within GENESYS, we have a property sheet. You can do it in terms of a SysML requirements diagram. We even have connectors into the Excel environment to be able to do the work in Excel. The next step, and if you remember in the process flow, we talked about the system definition, the black box view. Well, this is the system context. It's one level above that. This is that layer 0, the universe perspective, if you will. This is the top level. Everything gets built into this in the model. This basically captures the universe view of your system. The first thing you would add to that universal view is your system of interest. The warning here is, do not get trapped in only thinking of the system of interest. Do not stop here. Because if you did, you're not expanding that view to look at the interactions that your system has with its environment. So here at the next level, we add the external entities. In this case, you have the video drone system, and we've added the GPS satellite, the user, and the operational environment. The trap here is you could add everything in the universe to this context. You don't want to do that either, because you want to focus on what does your system interact with. The next step would be to define what are those connections between your system and those external entities that are of interest to you. And so you add those connections and very specifically and somewhat abstractly state that. So the video drone to GPS satellite connection, if you will, and that repeats for the user and the operating environment. System context can come in a lot of different views, and different views are used by different people for different meanings. The diagram I was showing is somewhat hidden down here in the corner, and here's the same diagram without images. An internal block definition diagram can be used to bring more information out as we detail the model out. A block definition diagram is again, another view bringing more information about how the system context is assembled. And then a simple hierarchy view that doesn't have a lot of context to it, but establishes a basic relationship and understanding. The next step we want to talk about is behavior development. So we're going to move to activity diagrams. And the system context, as I created above as a blank, I'd also start with a system context function that basically has nothing in it. That was the starting point. I'd add to that system context parallel branches. And these branches essentially say that things run concurrently. They're in parallel. And I create a branch for each element in the system context. To that, I would add a function block that basically says there is a function that element performs in that branch. At the very basic level, this is a functional model. I can simulate this. It wouldn't be very interesting. It would show you 4 blocks executing simultaneously. There's no interactions defined yet. And again, it's very basic functionality. Where do we want to go from there? Well, we want to detail out that functionality a lot more than just the basics. So we're going to go to use cases. So we're going to use this use case to refine the problem space. Initially, it looks very similar to that context diagram in that it identifies the elements in that diagram, the external entities, and then the system of interest in that diagram. It's a pretty straightforward display, much like the other one. I've got my system of interest and the external actors. What we're going to do to that is add some abstract operations so that we can explain what the system does. In this case, identify target, position camera, capture images, and you can see how the user will interface to certain things, and the GPS satellite in the operational environment will interface to other aspects of it. It serves to help us have a discussion about those particular operations and create activity diagrams, essentially threads, for those to explore what the system does. Other examples that aren't on here, you may identify, well, will it fly in rain? Well, maybe we want to do a use case specifically as a specific example to talk about this diagram and, well, will it work in rain? What about wind speed? What about low battery return, emergency low battery landing, flight range? Those are all things that we can talk about in use cases to further develop the functionality we need for the system. From that, and I'm going to specifically talk about the charging thread there, you develop a thread from that use case. And the thread becomes pretty much a sequential flow of operations from the start to the end of what you would want to have happen relative to that diagram. So we talked about the user on the one side. Well, if I think about it, the user is going to plug the charger into the system. And then, well, I put this here for a specific reason, but okay, provide the feedback that it's been connected. And then I'm going to plug in the charger itself. When I do that, I'm going to get an indication, indicate system charger connected. Okay, the user should acknowledge that. It's going to lead then to charging the system, acknowledge that the system's charging, or indicate the system charge complete, acknowledge system charging complete, unplug the system charger, indicate the charger's unplugged, acknowledge the charger's unplugged, and disconnect charger from system. It's just a sequential set of steps that you can think of as you execute that charging sequence. That gives you a basic flow. Where we go from there is we talk about what is the information that gets exchanged along the way. I deliberately put this charger feedback here because I was specifically thinking that when I plug it in, I want the user to know that it's connected securely. So this might be a mechanical feedback that it clicks when you plug in the charger. Now, as far as the system charging status, in my head, I had it as I was thinking through it. This is some sort of LED light that might be on the drone or on the remote control that indicates the status of charging. And so it might turn on at one point, it might turn off at another point, so on and so forth. But this is to get a definition of the inputs, outputs, and triggers across the flow. The next step in the process would be take these functions and identify who or what is doing the work. And so as you can see, I've highlighted here in two different colors, the user and the video drone system to demonstrate that. This gives us a very basic functionality. This is a top level view. It's high level. We can break this down at the next level. We're not going to do that here, but you could. That would be the next step. This gets us to that first layer kind of view. I would create multiple threads to get us there. We're now going to talk about the physical architecture. And so as I showed earlier, this is the system context level. You have the system context at the top of the block definition diagram, and you then have its components. As we move the layer down, you might take that system of interest, the video drone system, and break it down further. I have a remote control, the drone, the phone app. The block definition diagram shows the hierarchy. The physical block diagram that I've shown there shows interfaces. So it'd be a Wi-Fi interface or an RF interface. So you can start to see the different diagrams present different information. But this is now the first glass box view, if you will, because we're looking inside the system of interest. The system is the full drone system. You can take this to the next layer, and you can take the drone and break it out into its components. And this is really going to be the focus as we move forward, is going to be on the drone. But as you can see, battery, camera, flight controller, motors, sensors, antennas, etc. I can even go another layer if I want. So the flight controller, I could go into CPU, GPS memory. At this layer, it's not necessarily something the systems engineers would do, but could do. We have these discussions as a team with the other subject matter experts, and together we decide what goes in the systems engineering model. This was decided to be added so that this information can be passed off to detailed design as preliminary architecture work, so that they could start from that to work through the next layer of design. So if I go back up one layer, this becomes a interface diagram at the drone level. And this is really what's important for the wiring harness discussion. We've laid out the architecture from a component standpoint. We've defined the connections. And this is not every signal here, but it is a relative connection. And we're able to uniquely identify different types of parts, different types of connections. In this case, the red would be power connections, the blue would be signals, the green would be communication network signals. So you can uniquely define that within the diagramming. Additionally, in this, we've added a port because we've decided we want to use a very specific connector, and that's reuse of an existing connector. So that's information you could capture in your system model. But this is the level of detail that we need to hand off to the detailed design team. So now on to the idea of taking your model and being able to share it with others, utilize it with other tooling environments, and really create that digital connection, that digital engineering work. So within GENESYS, we do have the ability to directly interface with DOORS, MATLAB Simulink, and Model Center. There are additional connectors we have created. You'll see these in the Excel, is that they show up in Excel, and you can access the data from the GENESYS database directly in Excel, Project, and PowerPoint. There's an underlying set of standard API that use the .NET framework, and you can create your own connectors to that database. The meta model that I talked about at the beginning is a schema, and it is extensible. You can create and modify that schema so that you can interface to other tools. The E3 series connector, we've modified component link import so that we can pass the right information off to the detailed design team to be able to do their wiring harness designs. The last is a team view in HTML, It's basically an HTML export from the database so that you could publish this and anybody could view the model in a web browser. So just to recap, I did a quick review of the systems engineering approach. We went through the building of a systems models through requirements capture, system context definition, behavior development, threading, physical architecture. And then I covered some information about how to share the model. So now I'm going to move into a demonstration, and it's going to go through various steps. I'm going to go through kind of a quick overview of the model, much like we, similar to the slides that we presented. I'm going to add a utility company to the system context. I'm going to add a utility company to the activity diagram. We'll add the utility company to the system use case. We'll add provide power function to charging thread, and we'll show updates across view. Now, I put them in that order because that would be the normal systems engineering process if I had thought about it up front. I'm actually going to start with provide power and work back because it's the use case that identified this gap. After we show the updates, I'll do a quick demonstration of team view, and that'll be the completion of the demonstration. So let me go ahead and escape out of the presentation. And I will bring up GENESYS. So this is the GENESYS environment. Pretty straightforward. It has a project explorer and then a description pane. We're going to quickly go through, much like we did in the presentation. I have requirements. We talked about the video drone size. And here's an example of it's basically the requirement. It needs to be compact enough. I can very quickly change to a requirements view, requirements diagram view. And this just gives you kind of a hierarchy. That first level requirement, I rewrote it again for size. I broke it down, and I know it's not readable. We can zoom in and out to make it readable. The goal was to kind of show you how these diagrams come together. Not only do I see my requirements, I can point to the component that's going to satisfy that requirement. I can also point to verification requirements. So that's kind of a quick overview of requirements. I'm going to bring Excel over. The same information can be viewed in Excel, and the connector, when you install it, will create a GENESYS tab in the Excel spreadsheet, and you would have the ability to interact through this. Not only can you pull the data out, you can modify it and publish it back to the database. So that's the requirement side of it. Talk about the system context, and I'm going to specifically look at the physical block diagram. So this is the generic view of it. The nice thing about GENESYS is that I can go through and create multiple views. So all the views I used in the presentation, I have saved so that I could quickly flip through those views. But they all come from this base view as a starting point. If I update this, it'll update those other views. It's one of the beauties and powers of GENESYS is that it maintains that data across views, minimizing the amount of work that you have to do to update the drawings, because the drawings are just views of the information model. So that's that. Functionally, the system context model, and you will see the activity diagram. This actually starts to show data items that interact between the components. I have the same view that was in the display or in the slides. Use cases, same type of thing. I can create multiple views and maintain and save those. Threading. The charging behavior thread and the activity diagram here. And this is where I'm going to start the modifications. And so, as I said, you know, you look at this flow and we find that, hey, there's something missing. Yeah, I plug in this charger, but how do I indicate that the system is, you know, system charger connection status? Well, it's a light. Well, where am I getting the power from? What am I plugging into? So we're going to add a new function here, and it's just going to be provide power. It simply adds it there. Now, maintaining common diagrams, activity and sequence diagrams are very similar. And I just added that, and you can see that it added it in the activity diagram or the sequence diagram as well. On the other side of it, I'm going to say unplug it, and I'm going to have the function remove power. Okay. Well, those are the functions. Now I have something to interchange between these. And so I'm going to add to it an output. And I'm going to call that output, a new output called power. Now, this power, oops, becomes I can take that as an output and create it then as an input for each of the indicators. I'm also going to make it an output of the remove power function so that it gets updated by that. Because if at any point in time I were to remove power, I just have it here. But if I removed it at any point in time, any of those functions would no longer work. And last one. And so I've just added power to it. Now, you can see that there's no definition of who's done this, who's provided the power. Well, I haven't really added the components. So now I'm going to go back to the system context, and I'm actually going to add a new component to to the diagram, and it's going to be the electric utility. So now here it is on the diagram, and now I'm going to add a connection here. And it's a new connection. Now, as I said, it maintains these across view. So this was not hidden in my previous version of this. So it added it to that drawing as well. And it shows up there. It shows up here. So it will add that information and maintains your drawings one by one, or as you make your changes. So we talked about functions too. And when you look at the activity diagram, I can very quickly add another branch to this parallel by double clicking on it. And I can then take function, and there it is, perform utility function. Oop. Once is enough. And I've added it to my functional diagram. And again, the view, if I do it with no items, and again, this is executable. So we've added the power functions to the threads. We've added the functions to the higher level system context. We've added the component to the system context. So very quickly we can update the model and it maintains that information across views. So from that, the last thing that I wanted to show you was the idea of information sharing. And this is the web-based view of the model. And so if I take a system drone, I clicked on the component and I showed the drone design, you can show all the information related to this drone design, descriptions, relationships. So you can see that it's built from a number of components. It's built into the system context. It's connected through interfaces. It's constrained by some constraint definitions, which we'll show in the second webinar. It exhibits states. There's some packaging that's been done so that you can create certain displays, performs functions, and is specified by a number of requirements. This is the power of the relationships in that meta model, and the data is that it's all connected. And I can go click on the information to gather more information. This is a property sheet view, and you can see a number of diagrammatic views as well. I'm just going to do the internal flow internal block. So this is the one that we talked about a little bit. It'll be used in the detailed design. So that concludes the demonstration. Bob, I'm going to turn back to you for the last polling question.
All right, thanks, Steve. So the last polling question is, what systems engineering tool are you using or considering today? Core or GENESYS, Cameo, some tools from the Microsoft suite, Visio, Excel, Rhapsody, or are you using another tool? And again, we really appreciate the participation. Thank you, and I'm going to let this run a few more seconds. This is very good information. Thank you. Appreciate your, again, your participation. All right, I'm going to let this go for a few more seconds. All right, let me go ahead and close the polling and we'll share those results. So what systems engineering tool are you using or considering? Looks like a good distribution here. We've got Core and GENESYS sitting at 32%, Cameo at 41%. We have Microsoft at 26%, Rhapsody at 14%, and other at 30%. Very interesting distribution. Steve, any comments?
Not really. I think that's pretty much in line with how the market perspective appears. It's good that you're doing systems engineering. It's good that you're using tools. It's advancing the art. So
Great.
Good information.
Yep, definitely appreciate that. Thanks for sharing, everyone. And I will hide that and turn it back over to you, Steve.
So I just wanted to quickly, what are the three things that I would like you to take away and walk away from this webinar with is, one, define and use your systems engineering approach. It's not one fits all. You have to define yours and use yours. Two, when you're doing your development, develop and evolve your problem space so that you're sure you're solving the right problem. Use your requirements, use that system context, use cases and behavioral threading to help you work through that problem space. Three, create your physical architecture in the solution space through functional decomposition and allocation. Too often we jump directly to that physical. Really work through the behavioral simultaneously. Don't just jump to your physical solution. So those are the 3 top takeaways I'd like you to walk away with today. Questions?
All right. So Steve, we've got quite a few from the audience, so I'm going to try to go through these more or less in the order they came in. So let's start with a question from Christopher. Christopher asks, what's the difference between the IBD and the PBD?
Oh, good question. So a physical block diagram is meant to be less content. It's meant to be a more general diagram used for a general audience. It really just depicts the physical components and their interfaces. Within the SysML notation in internal block diagrams, you can communicate a lot more information than just the components and their relationships. You can get into the components, their relationships, the individual pieces of data that are exchanged, the connectors, the ports. There's a lot more information that you can put in an IBD than a PBD.
Great. Another question from Brian. How have you implemented, sorry, just a moment, here we go. How have you implemented the delivery of SysML model views to stakeholders, customers, management, and engineering?
Good question. There are different ways to do that. Now, within GENESYS, it depends on what that exchange is with the customer. So we showed you the Excel connector. The connector to PowerPoint has a similar capability of being able to pull those diagrams out and dump them in a PowerPoint presentation. GENESYS has the ability to create reports and populate both the diagrammatic as well as the textual information into those reports. So there's different ways. It really depends on how you're interfacing between your model and your customer.
Okay.
And one last thing on that is, as I said, there are APIs there that allow you to access the database, process the database, create a data file the way you want to create it, and deliver it to your customer in that way. So you can create an intermediate application from GENESYS to your customer if you want.
Okay, thanks, Steve. A couple of questions from Guy. How many requirements can you put in the system? 100, 1,000, 10,000 is the first part. So why don't you answer that, and then I'll give you the second part.
My answer is I'm not sure. I know it's in the thousands. I just don't know the absolute limit of it. So the system can. So okay, I can try to get that information later, but I don't have a hard number. Sorry.
That's fine. That's fine. Part 2 of Guy's question is, can doors be connected to GENESYS?
Yes. We have a built-in connector in GENESYS. And it's a bit of work to get the two to talk, but you can. So there is direct connection. You really want to make sure you define who is the master of that data so that you're, when you're talking about backing up and maintaining it, that there's only one master of the data, but the two exchange the data.
Okay. Thank you.
And there will be a webinar coming up on that, so we'll be sure to share that with the Zuken webinar series.
Okay. The questions keep rolling in here. I'm going to try to, again, kind of get through these. We're running short on time, but I'm going to try one here. This one's from Ali. As a mechanical engineer, how does this tool, how can this tool help design products better?
So it's a hard translation from systems engineering into the mechanical world in some senses, because in the mechanical world, we tend to think more in characteristics than we do about behavior. An example, you have a anti-roll bar in your car, and they talk about stiffness. Well, the real function of that anti-roll bar is to transfer force from one side of the vehicle to the other. And so when we start to look at the functional nature of it and use functional names to describe what's going on in a systems engineering world, we can do a better job. And this is not, again, as I said, by a single systems engineer. This is using your subject matter experts across disciplines. I pull in the mechanical engineer, have those discussions. What really is the function of that? And I may put it in my language of transfer force, but I've also got to relay it back to him. Hey, I need a connector rod, and it's got to have this stiffness to it. That might be the context that I work with my mechanical engineer. A large portion of systems engineering's job is to communicate the information in the right way to the rest of the team. We are that connective tissue between the teams and want to be sure that the information is flowing freely back and forth.
Great. Very good answer. Thanks, Steve. I've got a question from Stephanie, and this could be a kind of a big question. Please describe the functionality of GENESYS versus the Dassault systems. I'm assuming Stephanie means no magic, which I believe they call CATIA magic
Cameo.
today.
Yeah. Stephanie, I wish I had a full answer on that. I haven't worked too much with the Dassault system, so it's hard for me to do that, but we can get you that marketing information that compares those two. What I can say is that my experience with Cameo has been, it has been very different in that it's a SysML tool, not a systems engineering tool. And I don't want that to come off wrong, because you can do systems engineering in the Cameo tool, but the basis of it has been SysML. And SysML is 9 disconnected drawings without that meta model underneath to connect them. And to drive the views rather than the views being the center of the tool, it's hard to create that system model. Can that same thing be done in Cameo? I believe you can create that meta model underneath it in Cameo. I believe you can connect things. I don't know that we'll auto-generate your drawings for you from that model. I think it's the other way around. But that's my understanding of Cameo. So GENESYS provides you an integrated environment where the focus is building that meta model, and the views come out of the meta model. You can use the views to create the data and instantiate the data, but the views are secondary. We as engineers want to be doing engineering work, not drawing work.
Okay, and Stephanie, as Steve said, we're happy to follow up in more detail with a secondary conversation, as is the case with all the questions. If you feel like we have not answered the question with enough detail, we are happy to do a follow-up, and we'll be reaching out to all of you. We have time for just a couple more questions. I've got one from Don. In your presentation, there seemed to be an immediate jump to a selected system solution. What are your thoughts about how to create an optimum system solution before using SysML?
Thoughts of creating an optimum system solution before? Well, optimize for what? Because that's the challenge. When we say optimize, we need to really understand what are the constraints under which we want to try to optimize.
And Steve, let me jump in because I'm wondering if this question could be better answered by our second webinar, where we really look at optimizing the architecture and the design based on business value. Is that fair?
Yeah, it's kind of where I was going to go, is that you know, it's about the functional behavior. And once we have a good enough definition of the functional behavior, we can hand it off to analytics. And analytics can do a lot and bring back suggestions and information back to the system model. Again, the SysML is a set of views. And this isn't about the views, it's about the fundamental functional behavior and design, the architecture, the descriptive architecture of your system.
Okay. Very good. Very good. Unfortunately, I think we have time for one more question. And as I said, we will follow up with everyone. I did have a question from Brian. Is this tool used to design other than physical products? So for instance, an IT infrastructure or a business process?
Yes. The same meta model can be used to describe an enterprise architecture. So your organizational architecture, your process architectures, and so on. You can use the same tool. It's been used to do regulatory investigations to determine the impacts of regulatory requirements on outside organizations. It's been used in a lot of different ways. But if you think of any given system, a system does, it's a behavior, and a system is. That could be a process, a person, a component. There's a document. So you can use it to describe pretty much anything.
Very good. All right, thanks, Steve. Unfortunately, we are out of time, and I'm going to have to wrap up the webinar. As I said, we will follow up with all the individual questions. And just a reminder that if you haven't signed up for the part 2 and part 3 of this webinar series, part 2 is going to look at the trade studies and optimizing the model for business value. And part 3 will actually move the model into detailed design, creating a wire harness. So again, thank you all so much for attending today. As you exit, we're going to ask you one quick question to tell us, please tell us how we did today, so we can always try to improve the webinar experience. Thank you all again. Have a wonderful day.